This lecture is about water conservation, particularly in small communities. Canadians are some of the largest water users, and most of the cities are metered and account for water in a reasonable manner, but small communities are in most cases not metered and really don't have very good data. So to show you some of the challenges we face by trying to focus on water conservation, we had this opportunity to actually look at 14 mountain communities over a 7-year period to see what kind of challenges these communities have in order to achieve significant water conservation and reduction in consumption. So I'm going to give you a short introduction to water conservation and then show you the project which we carried out in the Columbia Basin. We then look at what is happening to the climate in the world and also in this particular region. Then we go into the conservation, some of the financial issues, and a bit of a summary. So why do we need water conservation? Well, the demand for water is increasing, supplies are becoming more variable, and we also need to leave enough water for the environment to function for environmental services. The demand for water is increasing not just in mining and recreation, but also because of massive urban population increases. And of course, climate variability is creating all kinds of new issues which we have not previously need to consider. So if you look at the global population in green and the rural population in red and the urban population in blue, you can see right now we are about 55% urban, and the projections are by 2050 this will be 70%, which means between now and then 2.6 to 2.8 billion people move into cities, and you can imagine the demand for water will obviously increase unless we go to massive conservation measures. So if you're water short, you have 4 options. You can either enhance storage, you can conserve, you can look for new water sources, or you can recycle and reuse. Enhancing storage is usually quite expensive. Conservation is probably the most cost-effective short-term solution, but it means we have to change behavior, which is a new challenge. New water sources are becoming much more difficult because all the easy water sources are already being used, and the recycling and reuse the water is a technical issue because it requires replumbing and all kinds of new rules and regulations. In 2005, I sent a student around the Columbia Basin to talk to all the engineers and to figure out how much water are they actually using. And she came up with astronomical numbers, up to about 1,500 liters per person per day, and we figured this can't be right. Most of these communities had very poor metering systems and had really no good accounting for water. So the Columbia Basin Trust in 2009 decided they would initiate a water conservation program, and they asked the communities whether they would like to participate in a 20% water reduction over a 7-year period, and 14 communities did the project in a consistent manner that we were able to actually compare the data. We had 12 climate stations which were very close to each of the communities, which we could use in order to actually do the comparison. To give you an idea where the area is located, that's the West Kootenays, the East Kootenays. We had a number of communities in the northern part of the mountains, in a number of them in the southern part, 3 of them in the Rocky Mountains, and obviously the East Kootenays were between Cranbrook and Golden. So the key factors for conservation are simply climate, land use, human behavior, management, and technology. Temperatures and precipitation is an important part, because if temperatures are high and precipitation is low, we usually use a lot of water because it depends on how much outdoor activities you do. It also depends on your commercial activities and whether you're in a tourist environment or whatever. And of course, beliefs is a real big factor, because in the Columbia Basin people think water is plentiful and we don't really have to worry, so it's hard to persuade them to actually reduce their water consumption. So habits and incentives and regulations are required in order to change the incentives for conservation. Another thing is the capacity of the management people and the skills in order to maintain the infrastructure, and of course the type of infrastructure, its quality and its longevity is also very critical. So when we try to account for water consumption at the community level, we have 4 categories of water which is being allocated. One is what we call the ICI, which is the institutional, commercial and industrial water use. Then we have the non-reviewable water. That is the water which is used for firefighting and so on. Then we have the leakage component, and then the rest of it is domestic or residential water use. So each community has different proportions. You can see this community has a very high leakage problem and relatively low industrial, commercial, and industrial water use, whereas this community is quite different. So if you look at temperatures from the cold winter in January, February, March, all the way to the hot summer in July and August, you can see in the winter time these 3 communities use about the same amount of water, and it doesn't change with temperature. But as soon as you get to about 14, 15 degrees, the rate of water consumption changes quite dramatically between communities. So, for example, Trail in red has a very steep rate. As the temperature increases, their consumption increases dramatically, whereas Nelson in black has a much less steep curve. So, what is happening to the climate? Well, you all know that climate is warming. 16 was the hottest globally, 15 the second, and 14 the third hottest. What you probably are also aware is that the greenhouse gases have really not declined at all. In fact, in 2015, we reached 400 ppm of greenhouse gases over a 3-month period, and in 2016, the whole year was about 400, which means global warming will likely continue for quite a long time to come. So what is classic is we've made a big mistake. We've told everybody that the temperatures will increase between 2 and 3 degrees over the next 50 years. And typically what we do is we make a bell-shaped curve where these would be the extreme low temperatures and extreme high temperatures, and that's the mean. And what we forgot to tell people is, when do you really worry about water? When it's too hot or too cold or too wet or too dry, which means historically this is what the frequency of observations were. But what we're now experiencing is we're going to experience more extreme events at the low end and at the high end. So under the early assumptions, we basically said, well, here's the bell-shaped historic curve, and it's now getting warmer, so it's shifting in this direction, which means we're going to have virtually no more cold, extreme cold conditions, but we're going to have a lot of more hot conditions. But if we now look at this increased variability, so that's the old curve, and that's now the new curve where the extremes have actually increased, which means, yes, we're still shifting it, but this new curve means we still get a more number of very extreme cold events, but much more hot events. So is this actually happening? If you look at the extreme hot temperatures per decade in red and the extreme cold temperatures in blue on a decade basis from 1920 to 2010 in the United States, you can see that in the 30s when we had the drought, yes, we had far more hot extreme temperatures and cold temperatures, but look at what has happened between 1980 and 2010. Each decade we had an increase in extreme hot temperatures and we had a decrease in extreme cold temperatures, but we still have at least 30% of the events as extreme cold. And if you look at what has happened this last winter, this is clearly an indication that some of these events are happening, but they happen at a less frequent time. What are more evidence of this kind of extreme events? Here is an example from the insurance company. They said, well, the number of floods since the 1900s have gone from virtually a few to 19 in 2016, the highest ever. And if you look at the rainfall events, the daily rainfall for most of the United States, you can see that the trend over the last 10 years has been that we're getting more intense rainfall events over a one-day period than ever before. Just to show you how these extreme events happened over a very short time period, you know California had a big drought. At the peak of the drought between 13 and 14, this is the average precipitation over a 100-year record for these northern climate stations in Northern California. In the 30s, we had the most extreme drought, so the discharge or the precipitation was at the lowest level ever. During the peak of the drought in California, this is how much precipitation happened, so a large reduction in precipitation. Moving forward to now, 16 to 17, you can see we're now at a situation where we are above the most wettest year ever recorded in California since the 1900s. So we have gone from an extreme drought to an extreme flood. And if you looked at the latest news, all kinds of flooding events are happening in California right now. So again, this shows you that these extreme events are actually happening. Another example is Boulder, Colorado, a 100-year record of precipitation in September. Look what happened in 2013, a massive rainfall event, and the details for that are as follows. In one day they get 230 millimeters of rainfall, and if you take 3 days between here and there, this is the 1 day precipitation, the 2 day and the 3 day precipitation. So in 3 days they got 341 millimeters per rain for the months of September, and the annual average is about 485. So in 3 days they got 3/4 of the annual rainfall, and the average in September is about 43. So that's obviously a very extreme event. So now let's look what is happening in the Columbia Basin. Here's Caslow. This is the millimeters for the months of June from 1913 to now. The highest precipitation occurred in 1965, and in 2005, 2012, and 2013 we had 3 events which were between 30 and 70% higher than anything we have ever experienced. If you look at variability, you look at Caslow's precipitation over the historic record, you can see in the early days the variability was much smaller than it is now, which means we're going to have to really start thinking about how to cope with these unusual events. In 2015, it was one of the driest in 100 years. So Alan Hamlet at the University of Washington did an interesting study in the Pacific Northwest, where he used 12 global models to project what is happening to temperature and precipitation using the historic record and then projecting it to 2100. And if you can see, the temperature all goes in the same direction, and there is a difference between the models of about 3 to 4 degrees, but all of them are going in the same direction. It's getting warmer. But when you look at the precipitation for the same area, some of the models are telling us it's going to get 25% wetter, and some of the models are telling us it's going to get 20% less wet. That almost a 50% uncertainty, which makes it very difficult for decision makers to actually decide what we're going to do. And I would argue in these mountain environments we have so many microclimatic conditions that I don't think we're able to really make good predictions on precipitation. So here are the 12 climate stations which we used for the study. Here are the northern ones, the southern ones, and the Rocky Mountain ones. And the June precipitation, the June temperatures over the 7-year study period are indicated here. And what I'm showing you here is the mean temperature for the months of June and the precipitation for the months of June. And all the blue dots are a 100-year record. And you can see over this period over which we did the study between 2009 and 2015, we had one of the hottest years and two of the wettest years ever in 100 years. And this was true for a number of these communities, not all of them, but a number of them. And just to make sure, we can actually tell you that over the study period, about 7 of the 10 stations had the hottest or the fourth hottest temperature in 2015, and about 8 of the 10 stations had the wettest precipitation ever. 2 examples from Caslow and Nelson. Again, mean maximum temperatures versus precipitation for the months of June. 2012, 2013, some of the wettest periods ever, 15 the hottest. And in those cases, we had massive flooding in both of these communities. And in Caslow, the 2013 event actually destroyed the water intake of their drinking water supply. So you can see these extreme events have huge impacts on how we manage the water. What is also important is the fact that if you look at the extreme minimum temperature, the mean minimum temperatures, the mean temperatures, the mean maximum temperatures, and the maximum temperatures for the months of January in golden, the maximum temperatures really haven't increased very much, but it's the extreme minimum which has increased dramatically. And this is quite important in these mountain communities, because once these minimum temperatures come up to close to zero, then we shift from snow to rain, which means the runoff in the rivers is going to come much earlier, and that means we're going to have less water in the late summer. How does this compare between communities? Well, here's the example of Nelson. You can see in December, January, and February, some of these minimum temperatures have actually increased by 10 to 11 degrees. And if you look at some of the other communities, you can see this is actually the pattern in many of the mountain communities, except for Caslow, which is located on the lake, a large lake which has a very moderating influence on the temperature increases. What is also important is look at the red bars. In all cases, the summer maximum temperatures really haven't increased very much. So it's really the winter time which is critical. What has happened to precipitation? This is the West Kootenays and the East Kootenays. There's a huge difference between the two regions. In the West Kootenays, precipitation has actually increased almost every month in all cases. Whereas in the East Kootenays, you can see that December, January, and February has actually resulted in significant decreases in winter precipitation, and the summer precipitation is still increasing, but at a much lower rate. If you then look at the snow, the red is the decline in snow, the blue is the increase in snow. So in the West Kootenays, you can see there's still a bit of increase in the early winter, but in the late winter, things are declining dramatically, and again, that's due to the increase in minimum temperatures. If you look at the East Kootenays, you can see we're looking at a significant decline in snow accumulation in all winter months and in all stations. That gets me to the way we do stormwater assessment. We usually use a 100-year storm as the reference on how much water is going to be generated. So the blue dots here are based on a historic event. So the largest event happened every 100 years, and this is how much water it generated. But since we now have totally different conditions, you can see we now have to readjust this to the red line, which means a 100-year storm might occur every 8 or 10 years. And this means we need to really think about how to deal with this in a different way. So let's now go to the conservation again to remind you here the communities. Environment Canada did a survey in 2011 and published it in 2014, where they looked at all rural communities, the small ones, the medium size, the large ones, the Canadian average and the BC average, and they had some of them which were metered and some of them which were not metered, and these are the rates which the average rates which they came up for total water use. So you can see the difference between metered communities versus unmetered communities is quite dramatic. In fact, it ranged anywhere between 18% on average in BC to 52% average for medium-sized small communities. So metering is obviously important, and of course the big challenge is if you're not metered, how do you actually decide how much is ICI, how much is leakage, and how much is actually domestic water? So what you want to do is you want to find out how do you actually determine when did the lowest water use occur and when did the highest water use occur. And if you're interested in fixing leakages, you need to really do this when the lowest water use occurs. And this usually happens in November and February, and which means you need to go out there between 1 and 4 a.m. to measure when nobody is using water, to measure the system to see how much water is actually being lost. And if you're interested in the extreme summer, you want to know when do people use most of the water, and you usually should do this either in August or July. So if we now look at the temperature again, I mentioned before, in the winter time, water consumption is pretty much the same. This is the data over the 7-year period of the study. And you see winter time, virtually no change until we get to about 14, 15 degrees. And then massive increases depending on the community. So let's have a quick look at individual communities and see how successful they were in changing their water consumption. All the blue dots are the data for 2009 to 2014, and the red is 2015 when we had this really hot summer. So in this community you can see that in the winter time it was pretty much the same, and in the summertime these people were able to actually reduce their water consumption quite a lot in spite of the fact that it was very hot. And the reason for that is they were not only able to reduce their consumption in the summer, but they were also able to reduce their consumption in the winter, mainly because they went to universal metering. How did the other communities fare? Well, let's have a look at some of them. Here is a community who virtually was unable to do very much at all. And here is a community which was able to reduce their water consumption on an annual basis, particularly over the winter and the summer. Again, this community went to universal metering, and that's likely the reason for their success. Here is another community which shows a completely different pattern. They actually use more water in the winter time than in the summer, and had virtually no effect on the hot summer. And the reason for that is very simple. This is a mountain community up in the Rocky Mountains at high elevation. They bleed their pipes in the winter to prevent them from freezing, so that means the water runs 24 hours a day. And this obviously means that their water consumption in the summer is actually higher than in the winter is higher than in the summer. Similarly, Fernie has huge variation in water consumption, mainly because they also bleed their pipes, and also they have lots of leakages to deal with. Let's go to this community down here. This is Caslow. 2009 to 2013, you can see pretty much the same pattern. Then all of a sudden, the last 2 years, they were actually able to reduce their water consumption in a dramatic manner. And the reason for that is they had a massive leakage in the main distribution pipe. Once they fixed that, they were able to achieve massive conservation. So you can see each community has different issues associated with it, and if you display this in this way, you can actually show the different behavioral patterns. So we can now do something interesting. We can say, well, the winter time is pretty much the same, but the summertime changes depending on the community. This is Trail, this is Nakusp, and this is Nelson. So again, if we do a regression of the temperature increases for each one of these communities, we can actually predict how much more water they use for every degree increase above 14-degree temperature in the summer. And if you do that, you can see all of these regressions were significant, and that meant that many of these all these regressions were significant, and we can then decide that for every 1 degree of temperature increases above 14 degrees, Nelson uses 19 liters more water, whereas Trail uses 80 liters more water. So obviously these groups here, they need to start focusing on summer water consumption, because they obviously have a very steep increase with temperatures. And then you look at Ericsson, where they actually increase the water consumption by 436 liters per person for every degree temperature increases above 14. How do you explain that? Well, they have a residential or a domestic water system which supplies water not only for the community but also for agriculture. And as you know, agriculture uses much more water. Hence, we need to start thinking about maybe separating the two systems. So if you look at the regressions for temperature, they were all significant, and that helps us to actually show how much more water each community uses. But we should also consider precipitation, but this is a bit more challenging, because in the summer, if it rains, you obviously don't use as much water, but rainfall in the summer usually happens over 2 or 3 or 4 days, and since we only had monthly data, we weren't really able to do that, and you can see none of them or few of them were actually significant. The other thing which is also important is the total precipitation in the summer in the mountain region is actually the highest in June. So when you look at this, obviously in June people don't use very much more water because you get a lot of precipitation. So we could actually project the mean total water consumption for each one of these communities in red, the extreme maximum consumption in the summer, and the extreme minimum consumption in the winter. You can see that Nelson is doing quite well. Their difference is very small, whereas Trail has huge differences between summer and winter, and they need to focus on both of these things, whereas this community has to focus on summer consumption. The same thing here, whereas this community and this community, they really have to look at both ends. If you then look at the water consumption on a monthly basis, you can see June, when you get lots of precipitation, usually for all communities, the water consumption is much lower. How successful were they in conserving? This is 2012, 13, 14, 15, and 16 15 in red against the baseline of 2009. So this community was very successful in reducing their water consumption by about 12% until the 2015 summer, which was hot and dry, and they obviously didn't have much restriction in place, so they weren't able to consistently reduce their consumption, whereas Rossland and Sparwood were actually able to, in a consistent manner, to reduce their water consumption year after year, and both of these communities went to universal metering. In contrast, this community was not able to actually increase their water consumption or conservation at all, and the reason for that is they had a major leak in their distribution pipe, which is going to take several years to replace, and as a result they were not able to actually reduce their water consumption. Here's an interesting case where they have had virtually no effect on water consumption from 2012 to 2013, but then a massive increase in conservation, mainly because that's Kaslo which fixed a major leak in the pipes. So each community had different rates of conservation success. We could look at this in terms of month by month conservation effort, the percentage of water reductions they had in blue, and the increases in yellow. So, for example, this community was totally unsuccessful in reducing their consumption almost over the whole year period. This community, mainly in the winter time, used more water, reduced it in the summer. So each one was different in their behavior. These communities weren't very successful, whereas these communities were extremely successful. That gets us now to the problem: how do we actually determine how much water is used for residential purposes? And if we do that, in the case of Ericsson, you can see we estimated that probably 30 to 40% of the total water use is for residential purposes, which means that anywhere between 700 and 940 liters per person per day. In contrast, Fruitdale doesn't have much industrial and commercial activities. As a result, about 60 to 70% of their water is being used for residential purposes, and that ranged anywhere between 350 to 417 liters per person per day. These are the communities went to universal water metering in 2015, and you can see both of them have very low water consumption, and so this gives us a bit of an idea how we deal with this. None of these communities were metered, so this is the best estimate we could come up with. So we could then show you in blue the total water use for each community and the municipal or the domestic water use, and they ranged anywhere between 233 to 517 liters per person per day. If you look at this in terms of the Canadian average, again, the blue is the total water use and the red is the domestic water use for the various provinces in Canada. They ranged between 189 to 395 liters per person per day. So you can see most of the rural communities still use far more water than they do in the more city-based conditions. Now, how do we actually account for leakages? Because these happen sporadically, and so Environment Canada in their national survey in 2011 determined the residential, commercial, industrial and leakage for these small communities, and they came up with a range between 9 and 12% for small communities of leakages. Well, if we then look at the Canadian mean in residential and our mean in residential, we could apply the ICI, the commercial and industrial rates, which the Canadian survey provided, to the Columbia Basin, and then we can actually determine the leakages, and in this case the leakages were anywhere between 26 to 43%. And this is corroborated by the engineers who actually did the leaking tests, and they figured in many cases up to 50% of their water was lost by leakages. So that gets us to the financial system, and the financial system shows you basically that if you are not metered, you charge a flat rate and you have unlimited use of your water. So, for example, here in Vancouver, the city isn't metered, and I pay $550 a year and I can use as much water as I want. If you now are metered, you can use this on a volumetric basis, and you can charge people according to how much water they use. Or you can even go to the point where you have a block rate system where you charge them according volumetric rates but based on different levels of consumption. So maybe the first 200 liters are at a low rate, the next 200 per day are a medium rate, and anything above is at the high rate. So if you don't charge enough for water, how can you actually have enough money to help if the infrastructure problem and leakage problem? So because only 2 of the 14 communities were metered, everybody has a flat rate at the beginning of the study, and these are the flat rates which they charged in 2015, and they ranged anywhere between $217 per year to $569 per year. Vancouver is at about $550. So you can see a huge range of charges, and basically flat rates means unlimited water use. Also, they have different rates for the ICI, and they do some interesting things, like they charge hotels for water use per room, and the average is about $130 per year, and it ranged anywhere between $66 and $203 per year. And they have some really interesting things, like churches have an average rate of about $346, and they range from $209 to $665. So huge differences in the way they charge. Even schools are being charged, and they're charged by room, and the rate there is $205 on average, and the range is $104 to $310. So it gives you a bit of an idea what the different financial situations are in these different communities and how much they charge. So how much do they actually charge for the residential rates? Again, we go back to what we estimated is the percentage of the total water use per community, and then we assigned the flat rate on a day basis. So this would be the dollar per cubic meter. So in this community it's anywhere somewhere between 26 and 35, whereas Fruitvale uses between 60 and 70%, and that's their rate, and Nelson is somewhere in there. So if we do that and compare that, these are the different rates which each community is charging, and it ranges anywhere between 44 cents per cubic meter, which is 1,000 liters, to $3 per cubic meter. Wide range. How does that compare to what we do in Canada and elsewhere? The US charges about $1 per cubic meter. Japan similarly, Canada about $1.50, somewhere in there. Europe about anywhere between $2 and $7. So if you don't charge enough for water, how can you actually account for full cost accounting and infrastructure repairs and so on? So that gets us to the summary. And so we had some real major challenges in water consumption. The biggest problem is really how complex it is to do proper water accounting. It requires that we monitor the system and we calibrate the system. We need to encourage universal metering, because we know that if you go for universal metering, not only can you account for it, but you can also make sure that as soon as people know how much water they use, they will change their behavior. Water loss management was the greatest problem in the community, because they have very old infrastructure and not a very good asset inventory and replacement plan. And remember, doing water loss measurements is quite challenging in these mountain communities, because you have to do it in the middle of winter between 1 a.m. and 4 a.m., which is quite a hazardous task. Equitable water pricing is a big challenge, and it's very difficult to do when you're not metered. Source water inventory is now becoming critical, and we need to plan and protect the sources, and in some cases enhance the sources. We need a massive education program, and this Columbia Basin Trust did this effectively by having an ambassador program where they had students hired in the summer to go house to house to inform people what they could do to reduce their water footprint. And a new challenge for these mountain communities is there is now an incentive to start producing more local food, for food security, and that means they're going to use domestic water, which puts more pressure on the water source. So what was accomplished? Only 2 communities of the 14 were unable to actually reduce their water consumption. All the other ones did quite a good job and were able to achieve somewhere between 3 and 39% reduction. Leakage was the greatest problem, and in some cases was somewhere between 30 and 70%. The hot and dry summer created some new challenges because several communities did not have water restriction programs in place. And again, when you have a dry summer, it's very hard to decide when does the drought start and how long would the drought last. So when do you initiate restrictions? 2 communities initiated universal metering, and they were the most successful in accounting for water and reducing their water footprint. And they also, of course, were looked upon by the other communities because most of them considered universal metering but said it was too expensive, and they were going to wait and see how successful these 2 communities are before they initiate this process. So the conservation options you have is you need to conserve water at all seasons, and if you meter it, you can actually account for it, and as soon as you meter universally the water use, you have a reduction of 30%. And we now have smart meters, which means you can remotely access the data on a day-by-day basis, and that's a much more effective way. In terms of costs, if you have volumetric-based block rates, you can actually equitably assign rates to individuals according to how much water they use. Universal toilet replacement program can also help you with reducing water consumption because a conventional system has 21 liters per flush, and the new flushes, the low flush flushes, are somewhere between 3 and 6, which means you can save up to 150 liters per day just by going to low flush toilets. Recycling of water and using of grey water is obviously a good thing. You can go to roof water harvesting and use the water for outdoor purposes. That helps you reduce the water. And of course, behavioral changes, which requires massive public education. So in the winter, we need to really focus on leakage, detection and repair. We need to start looking at a better inventory of all the piping infrastructure and have a plan to replace old infrastructure. We need to insulate pipes so that we don't need to bleed the pipes during cold winters. In the summer, we need to really reduce the peak water consumption by using rainwater or grey water for outdoor purposes, reduce the area of lawns or replace the lawns with xeriscaping. We don't need to irrigate lawns in July and August because the grass will come back very quickly in the fall after the rains come. If you maintain a lawn, at least make sure you have at least 30 centimeters of topsoil before you lay the turf, because this way the water can be stored in the soil and reduces the irrigation requirements by at least 30%. And make sure that automated irrigation systems are efficient and only operate during dry periods. I want to give you a small example on some of the challenges which happen elsewhere. This is the reservoir of Chapman Creek, which supplies drinking water to 25,000 people on the Sunshine Coast. Here is Vancouver. The Sunshine Coast is located here. It's a 35-minute ferry ride. Very popular area now since the housing prices are so expensive in Vancouver. These are the monthly precipitation bars, and this is the discharge of the river, so it peaks in May, and it's a snow-dominated system. That means if it gets warmer and we shift from snow to rain, that means this peak is probably going to move to earlier in the spring, which means we're going to have more drought problems. So what happened in 2012? In July, there was still snow up in the higher mountains. The reservoir was full, no worries. In September, it looked pretty precarious, and in October it was so precarious that they were considering using pumps to pump the last bit of water over the weir so that the people have enough water. The blue is the monthly precipitation on average over the last 50 years, and the red is what happened in 2012, and you can see we had normal precipitation until about June, and then in July, August and September, all of a sudden we had virtually no precipitation. That created this problem, but then fortunately they had this massive rainfall in October, and that bailed them out. What happened in 2015? Completely different story. Similar precipitation in the wintertime, but then an early drought from April, May and June and partly July. And fortunately, they put in water restrictions very early on, and fortunately they got a reasonable above average rainfall in August, so that they virtually didn't have to run out of water. But they were at the point in the mid-June and early July when nobody was allowed to use domestic water for outdoor purposes. So if you look at this in context, 2012 was a late summer drought, 2015 was an early summer drought, and in each case we had different challenges to deal with this. So what is going to happen in the future? First and foremost, you can see that the summer precipitation is actually declining, and so is the winter precipitation, and so is the snow, which means we're going to get less rainfall, less snow, and at the same time the summer temperatures and the winter temperatures are increasing. This means we're going to have some real challenges facing this region, because the minimum temperatures are increasing much more rapidly, which means more early spring peak flow and then much less summer drought. So this gives you a bit of an idea on the complexity of trying to initiate water conservation programs, and it's really the rural communities which are struggling the most, because the big cities do have enough tax base that they can actually use good accounting systems. Thank you.